Clear? Let's talk about the last sorting algorithm for today's class. Any doubts so far? Simple, right? Both the algorithms that we have seen. Okay, good. Now, let's talk about insertion sort. As the name suggests, you are inserting something, right? Or you are inserting the element at its correct place. Okay? Or you can say, as soon as you insert the element into the array, you are going to sort it. Correct? So by the name, you can understand it, or you can recall it as well. Like what is happening actually in this sorting algorithm. So let's see the idea behind this insertion sort. Have you played the card games ever? Like any friendly card games? Yes, right. So what you do? So whenever you get the cards, right? So first of all, you always try to arrange them properly, right? Let's say you have picked the first card, and that is 10. You pick the second card, that is 5. So what you will do? You will place 5 at its correct position, right? Then I pick the third one, king. Let's say it comes out as king. I will place it after 10, right? So what we are doing actually, as soon as you pick the next card, you will see, okay, where its correct position, you will place it here. Place it at that position, right? You pick the next one, find the correct, place it at that point, right? So are you getting the idea behind this insertion sort? And you have to repeat for all the cards. This is what we are doing in this algorithm as well. Let's see the illustration. We are starting from here. We have 40, 13, 28. Let's say one by one you pick the card. One by one you have the element. Let's say 40. It is already sorted. Only one element is there. So blue is indicating sorted. This gray is indicating unsorted part. And the yellow one or the orange one is orange basically. That is the unsorted to be inserted. So now you insert 13 next. What you will do? Place 13 at its correct position. Now you have 13 and 40. Fine. Next 20. Place it at its correct position in the next iteration. 30, 20, 40. Then you pick 8. Place it at its correct position. Understood the illustration? Let's talk about the implementation. How we are going to implement it. So what we are doing actually, whenever you get one element, you find its correct position, right? Let's try to think how the implementation would be. So you are finding the correct position, and once you find the correct position, what you are doing, you are also shifting the elements to the right. If you carefully observe here, you have shifted 40 and then you placed 13 at its correct position, right? Similarly here, you have shifted 40 further and then you placed 20 at its correct position. And then what you did, you shifted all the elements here, 40 as well, 20 as well, 13 as well, and then you placed 8 at its correct position. These are the two things that you are doing, right? Shifting of the elements to make the place, right? And inserting that element at its correct position. These are the two things. Let's see the implementation now. Let's talk about the implementation of insertion sort. This is the array given to you, or the list, and this is the pseudocode. Now, carefully see what we are trying to do. Let's try to dry run it. Okay, let's try to dry run it. For I from 1 to length of a minus 1, that means till the end of array. But from 1 we are starting. Okay, so this is your I now. Okay, key is equal to a of I. So a of I. So we are saying that key is equal to a of I. That means a of 1 initially, which is 2. That means in key we have 2. Okay, now j is equal to I minus 1. So j is present over here. Okay, now we have a while loop. We can have for loop also, no problem at all. That means nested for loops we can have, but here in the pseudocode we can have while loop also. So while j is greater than 0, so j is greater than 0, that is true, because greater than equal to 0 basically, because j is 0, right? Index is 0. A of j is greater than key. A of j is greater than key. The answer is yes. So while loop condition is true. What we are going to do here, carefully observe now. This is the step. A of j plus 1 is equal to a of j. You are shifting the element now. That means you will place something like this. You will have a of j plus 1. In a of j plus 1, you are storing a of j. That means, can I say you can intermediate step is this? This is what you are getting now, correct? And you have decremented j also. J is equal to j minus 1. So now j is being present at its, you can say j is equal to minus 1 now, correct? J is equal to minus 1. Now what you will do, again compare this while condition, it will become false because j is equal to minus 1, false. Now this is the step, a of j plus 1 is equal to key. So what you have done here, you have shifted the element to its right, and you have make a place for this lesser element, right, which is your key here. Okay, so a of j plus 1, j is equal to minus 1, j plus 1 is 0. That means at the 0th index, now you are having 2. You are placing key, right? Key is 2 here. Any doubt in this so far? Okay, let's proceed further. Now, we can say a will be incremented. Now, sorry, I will be incremented. I is this now. And now we have key is equal to a of I, which is a of 0, 1, 2. So, which is 4 here. Okay. J is always, we are starting j as I minus 1 always. So here also just one position, to its left. That is from where we are starting j. Okay. Now while j is greater than equal to 0, yes it is. A of j is greater than key. Yes, 5 is greater than 4, right? So what you are going to do? You will simply again shift it. So you will have something like this, 2, 5, 5. See, we are already storing the key element. So it is, we are not losing any information, right? So this is what we are going to have. J is equal to j minus 1. Now j is pointed over here, decremented the j. Now a of, so again, further we will compare. Carefully see this, because we have to find the correct position of 4, right? Further we will compare. Still j is greater than equal to 0. Is a of j greater than key? Is 2 greater than 4? No. This while loop will exit. Now we'll have this a of j plus 1 is equal to key. That means a of j plus 1, that means you can have 4 placed over here. Again, related with the card game, right? You shift all the elements and then place at its correct position, right? So you have to compare with all previous element. Yes or no? You have to compare with all previous elements. So we first compare with 5 and then we compared with 2 also. So now we are having, so we stored 4 here. Now we have this thing. Any doubt here so far? Okay. So then I will be incremented further. I will be present over here and j will be present over here. While j is greater than equal to 0, yes. A of j greater than key. 5 is greater than 6. No. While loop exit. Condition is false. A of j plus 1 is equal to key. A of j plus 1 is equal to key. And key is 6 only, right? Initially, key was 6 only. So it is at its correct position. Fine. Again, I will be incremented further. Same as j. So now we have something like this. Now carefully see this. This is will give you more clarity. This will give you more clarity. This one. Now I is here, j is here. J is equal to I minus 1. So j is here just before I. J is greater than equal to 0. Yes. A of j greater than key. 6 is greater than 1. Key is 1 now. 6 is greater than 1. Yes. So what do? You shift 6. A of j plus 1 is equal to A of j. So you shift 6 here. What do you get? You get something like this. And you decrement j. J is now present over here. Again, you will compare. J is greater than equal to 0. Yes. A of j, that is 5. 5 is greater than 1. Yes. Again, shift 5 also. You simply store 5 here. So what do you get? 2, 4, 5, 5, 6, 3. Right? And j will be decremented. So j is present over here now. 4 is greater than 1. Yes. Shift it further. Where should I continue? Do we have space on the next one? Okay, no. Let me continue here at the whiteboard. Will that be fine? Okay. So we have 2 comma 4 comma 5 comma 5 comma 6 comma 3, and your j is decremented, right? Okay. Again, so 4 is, we can say 4 is greater than 1. Again, 4 will also be shifted. So we will get something like this, right? And j will be decremented. 2 is greater than 1. Yes. So here 4 is greater than 1. Here 2 is greater than 1. So 2 will also be shifted. So what do you get? 2 comma 2 comma 4 comma 5 comma 6 comma 3. And j will be decremented further. So now j is pointing to -1. That is the index, right? -1. So while loop will exit, and what we will do, we'll simply say a of j plus 1 is equal to key. That means j plus 1, that means we are talking about this one. Place key here. Key is 1 here, so place it there. Is this clear? This is what we are getting now so far, right? Now I will be incremented again. So I will be present over here now. And you know, initially j will be present just before I. So again, so your key will be a of I. So now your key is 3. Is this clear? Again, the same steps will be executed. 6 is greater than 3. 6 will be shifted. 5 is greater than 3. 5 will be shifted. 4 is greater than 3. 4 will be shifted. 2 is greater than 3. No. So basically you will have, finally you will store key here. So you will be getting this thing. Can I say now it is sorted? Is this clear? This is how insertion sort is working. You keep on shifting the elements to find the correct position, to make the space for the correct element at its correct position, and then you place it there. So that's why we are calling it as insertion sort. Any doubt here, Aparna? Crystal clear? Okay, good. So let's talk about the analysis part. Outer loop is running how many times? Carefully see this, where the pseudo code we have. Oh, yeah. So this is the outer loop. How many times it is running? It is not starting from 0. It is starting from 1, right? From 1 to n minus 1, you can say. So how many times? N minus 1 times. Yes. So outer loop will run n minus 1 times. What about the inner loop? If you have the best case, when the array is already sorted, can I say if we have the best case, the already array is already sorted, can I say this while loop will never execute? Why? Because a of j greater than key will never be true. This entire while loop condition will become false. This while loop will never execute. You will simply have a of j plus 1 is equal to key. And that is, place the element again at the same position, right? You will keep on incrementing I. This while loop will keep on, will be false. The condition of while loop will always be false because array is already sorted, right? So can I say in that scenario, we can say in best case, it will run order of n times. The time complexity will be order of n times, right? Okay. So no shifting of data will happen, right? But what about the worst case when the array is reversely sorted? That means it is in the descending order. Then this condition will always be true. Then insertion always occur at the front, right? You will keep on inserting the elements at the front. So best case will be order of n, because only one time the entire iteration will be the entire array will be scanned, right? And while loop will always be false. So this is the best case time complexity. And for worst case, it is going to be order of n square, because swapping will be shifting of elements will be done and insertion will be done at the front every time in every iteration. So it is going to be order of n square. With this also you can understand number of comparisons and shifting. In worst case, 1, then 2, then 3, up to n minus 1. So it is going to be n into n minus 1 by 2, right? And best case will be No shifting will happen, just the comparison is happening, right? Just the comparisons, these are indicating comparisons, and up to n minus 1 terms. So one time the outer for loop will execute, and that's it. That is n minus 1 times. This is going to give you order of n times, and this is going to give you order of n square. Can we say that, in case of, if we compare all three algorithms, for best case, by default, insertion sort will perform well, right? It is going to give us order of n time. But what about the worst case? All three are same, order of n square. Even for average case also, all three are same, right? Let's see the comparison table also. So this is for insertion, bubble, and selection sort. Best case, order of n time, just now we have seen. For bubble sort, order of n square. If you apply optimized version by using the flag, then you can have order of n. By default, it is order of n square. Selection sort, in all cases, it is order of n square. And average is also order of n square. Worst is also order of n square in all three algorithms. Correct? Okay, I forgot to talk about this in bubble sort, right? Whether it is in place or not. Yeah. So what about, can I say it is also in place algorithm, right? In case of bubble sort, just the same, you are not using any extra space, it is in place. And what about the stability? It is stable. It is stable. Even if you have duplicate elements, why it is stable? Because you are just comparing the adjacent elements and you are swapping, right? So it will not happen that the relative order of the duplicate elements will change. No, it will remain intact. So this is stable also. What about insertion sort? It is also in place, right? It is also in place. Same array or list you are using to sort the elements, and it is also stable. It is also stable, right? Because you place, as soon as you insert the element, you place it at its correct position. So no problem in that. So both are in place. I mean, all three are in place, right? So when I say in place, that is helpful to find out the space complexity, right? Space complexity is simple, right? If you are using some extra array, right, then you can say it is order of n, space complexity, because that means you are consuming some extra space to sort the elements. Otherwise, it is going to be order of 1, no extra space. So space complexity always we talk about when we are saying whether we have used some extra space or not, okay, in any algorithm. Is this clear? So it is order of 1, in place sorting algorithm, all three. It is stable, it is stable. It is not stable by default, but with some modifications, we can make it stable as well, right? And as I told you, it is in place. All three are in place. Is this clear? These three sorting algorithms, you have these three basic sorting algorithms in your syllabus. The next two sorting algorithms, which comes under divide and conquer approach, we'll see in the upcoming class. That is merge sort and quick sort, and they are also very important as per your exam point of view. Also, they are better than these algorithms. You will find it out. Any